All right. Good morning, everybody. Once again, this is our second stream for today, and as you know, we will be reading Geeks for Gate. Let me turn on my fan and let me get the timer as well. All right. Just a second. Oh yeah, we are here. We did that. We did that. All right. I completed a linked list as well. If I'm not wrong, I just need to. I hope my voice is audible. All right. Yep, you can read this. Trees are foundational structures in computer science, serving as the backbone for numerous algorithms and data representations. Gate aspirants should be well versed in tree structures to prepare for the gate exam in 2024. I'm about to write Gate 2027, does not matter. This article aims to provide a concise yet comprehensive overview of trees, exploring key concepts crucial for a comprehensive understanding of the topic. To help candidates understand tree-based problem-solving scenarios, these notes provide invaluable insights and knowledge essential to success in GATE. Tree data structure is a hierarchical data structure in which a collection of elements known as nodes are connected to each other via edges such that there exists exactly one path between any two nodes. Basic terminologies indeed tree data structure. Okay. Parent node. The node, which is a predecessor of a node, is called parent of the node. B is the parent node of D and E. Child node. The node that is immediate successor of a node is called the child node of the node. Example D or children of B. Where is the tree in the first place? Okay, here. Nice. Root node, the topmost node of a tree, or the node that does not have any parent node, is called the root node of the tree. A is a non-empty tree, must contain exactly one root and exactly one path from the root to all other nodes in the tree. Left node and external node, the nodes which do not have any child nodes, are called leaf nodes. Okay. Ancestor of a node, any predecessor node of the path of the root to that node are called ancestors. Here we are ancestors of node C. Okay, where is he? Yeah, descendants. Any successor node on the path from the leaf node to the node. EI are descendants of node B. EI are descendants of node B. Yes. Internal node. Wait. Siblings, children of the same parent, are called siblings. DE are siblings. Level of a node. The count of edges on path from the root to the node. The root node has level 0. Hmm. The internal node. A node with at least one child is called internal node. With at least one child. Okay. Neighbor of a node, parent or child node of that node are called neighbors of the node. Parent or child node. Neighbor, okay. Never heard of that terminology. Subtree, any node of the tree along with the descendant. Okay. Boss. Alright, let's continue. Tree traversal techniques. We got in order traversal. So in order is like you will visit left and right and then the route. So 4, 2, 5, 1, 6, 3, 7. Yes. Pre-order traversal. You visit the route first. 1, 2, 4 and 5, 3, 6, 7. Yes. Post order traversal. 4, 5, 2, 6, 7, 3 and 1. Nice. Nice, nice. Traverse the left subtree, called in order. Visit the route, travel the right subtree. In the case of binary search tree, in-order traversal gives nodes in non-descending order. To get the nodes of BST in non-descending order, a variation of in-order traversal where in-order traversal is reversed can be used. Okay. You make a variation. Pre-order traversal. Visit the route, traverse the left subtree, called the pre-order. Traverse the right subtree, called pre-order. Pre-order traversal is used to create copy of the tree. Pre-order traversal is used to get. Okay, pre-order. Okay. Pre-order is used to create a copy of the tree. Uh-huh. Yeah, because you have a condition. One. Okay. I need to check this one out. How is pre-order traversal used to get a copy of a tree? Okay. Copy of a tree using it does not mean take pre-ordered sequence and rebuild the tree from scratch. Okay, it means traverse the existing tree in pre-order and create nodes in the same structure. So we already have the original structure available. Okay. So technically, you can use an order and force order to copy a tree. All right. We kind of understood the philosophy behind copying a tree using pre-order traversal. Post order traversal left subtree, call post order, traversal right subtree, call post order, visit the root. Post order traversal is used to delete the tree. Yeah, because you delete the child. Nice. Nice. Things are making sense. We have binary tree, ternary tree, n-ary tree, or generic tree, binary search tree, AVL tree, B tree. In a binary tree, each node can have a maximum of two children linked to it. Some common types of binary trees include full binary trees, complete binary trees, balanced binary trees, and degenerate binary trees. We are going to look at each one of those now. A binary tree is full binary tree if every node has 0 or 2 children. The following are examples of a full binary tree. We can also say a full binary tree is a binary tree in which all nodes except leaf nodes have 2 children. A full binary tree is a special type of binary tree in which every parent or internal node has either 2 or no children. It is also known as a proper binary tree, degenerate or pathological tree, a tree where every internal node has one child. Such a tree or performance-wise same as linked list. A degenerate or pathological tree is a tree having a single child. Degenerate. Degenerate tree. Okay, kind of like a skewed tree. Yep, that is what came to my mind when reading the theory in the first place. Skewed binary tree. A skewed binary tree is a pathological or degenerate tree in which tree is either dominated by the left nodes or the right nodes. Thus, there are two types of skewed binary tree: left skewed or right skewed. This is actually an edge case that is asked in gate question. When I saw tree, I marked off, log n, but actually that is not the case. In a skewed binary tree, the maximum time for searching an element is O of n. Complete binary tree. Now, binary tree is complete binary tree for all the levels are completely filled, except possibly the last level, and the last level has all keys as left as possible. That is a complete binary tree. So you are arranging the elements like this from left to right. Perfect binary tree. A binary tree. A binary tree is perfect tree if all the internal nodes have two children or all leaf nodes are at the same level. Is there any difference between full binary tree and a perfect binary tree then? Okay, so there is a difference. Makes sense. Ouch. Yeah. Thank you. Balanced binary tree. A binary tree is balanced if the height of the tree is O of log n, where n is the number of nodes. For example, ah, the A will tree maintains O log n height by making sure that the difference between the heights of the left and right subtrees is at most 1. I have studied A will tree, so I know what this thing is talking about. Ternary tree is a tree data structure in which each node has at most three child nodes, usually distinguished as left, mid, and right. Kind of like ternary means three, ternary operator. An array tree or generic tree. Generic trees are a collection of nodes where each node is a data structure that consists of records and a list of references to which children. Duplicate references are not allowed. Unlike the linked list, each node stores the address of multiple nodes. An array tree like 4 array, 5 array, something like that. Binary search tree. Binary search tree is a node-based binary tree data structure which has the following properties. The left subtree of a node contains only nodes with keys lesser than the node's key. The right subtree of the node contains only nodes with keys greater than the node's key. The left and right subtree each must also be binary search trees. That's like the recursive step. Insertion, searching, and deletion. A new key is always inserted at the left by maintaining the property of the binary search tree. Okay. We start searching for a key from the root until we hit a left node. Once a left node is formed, the new node is attached as a child of the leaf node. The below steps are forward where we try to insert node into the binary search tree. Check if the value to be inserted, say x with value of the current node we are in. If x is less than value, we move to left subtree, otherwise we move to right subtree. Once the leaf node is reached, insert x to the right or left based on the relation between x and the leaf node's value. Uh-huh. So, and this thing here, there may be cases in which yeah, exactly. Suppose we need to insert 17. Yeah, this one. 20 is not a leaf. Yes, it is slightly misleading. So we have understood it. Once the leaf, should we mark that? Right. Not a major mistake. Straight. Wait, wait, that's gone like that. All right, I don't want to type that whole thing again. Did we get any mail from them? I just need to check that. Jan 20. No. Alright. At least we understood what we are reading. Time complexity of which where each is the height of the binary history. In the worst case, we may have to travel from root to the deepest tree, if not the height of the stew tree may become n, and the time complexity of insertion operation may become O of n. Wow, see, this was written and this was directly asked in gate auxiliary space O of n if we use an iterative approach n and as we use recursive approach. Yes, sir. Searching in BST. For searching a value in BST, consider it as a sorted array. Now we can easily perform search operation in BST using binary search algorithm. Let's say we want to search the number x, we start at the root, then we compare the values to be searched with the value of the root. If it is equal, we are done with the search. If it is smaller, we know that we need to go to the left subtree because in a binary search tree, all elements in the left subtree are smaller and the elements in the right subtree are larger. Repeat the first step till know what traversal is possible. If at any iteration key is found, return true, else false. Time complexity of which, where h is the height of the BST, auxiliary space, the height of the auxiliary space complexity of searching is infinite. We use an iterative approach or when as we use recursive approach. The task is to delete a node in the VST can be broken down into three scenarios. Delete a leaf node in a VST. If the node to be deleted is a leaf node, it can simply be removed from the tree. The parent node of the deleted node must have its corresponding child pointer set to null to reflect the change in the tree. Uh-huh. Deleting a node with a single child in BSD. If a node to be deleted has only one child, the child can be promoted to replace the deleted node. The parent node of the deleted node must have its corresponding child pointer updated to point to the promoted child. Okay, these cases we have seen delete a node with both the children and BSD. If the node to be deleted has two children, the replacement node can be found by either selecting the minimum value from the right subtree or the maximum value from the left subtree of the node to be deleted. This is actually called the higher order successor after finding the replacement node. After finding the replacement node, it can be promoted to replace the deleted node. The left subtree of the replacement node, if it exists, must be attached to the left child of the promoted node. The right subtree of the replacement node, if it exists, must be attached to the right child of the promoted node. The parent node of the deleted node must have its corresponding child pointer updated to point to the promoted node. Obviously, because we don't want to break the link of the tree, right? Time complexity is O of h. Auxiliary space required is O of n. The difference between the heights of the left subtree. Alright. We kind of skipped that AVL tree definition. Yeah, we are here. We just need to complete AVL trees and we will get this thing done with an AVL tree defined as a self-balancing binary search tree where the difference between the heights of the left and right subtrees for any node cannot be more than 1. The difference between the heights of the left subtree and the right subtree for any node is known as the balance factor of the node. Rotating the subtrees in an avial tree may rotate in one of the following four ways to keep itself balanced. Left rotation. When a node is added into the right subtree of the right subtree, if the tree gets out of balance, we do a single left rotation. Alright. Right subtree. Or maybe for clear distinction you can write right child of a left subtree. For a clear distinction and less confusion, we can write right child of right subtree. Okay, got it. If a node is added to the left subtree of the left subtree, then they will trimming it out of balance. We do a single right rotation. A left right rotation is a combination in which first left rotation takes place after the right rotation executes. First left rotation. Nice operations include insertion, deletion, and searching. Yes, we kind of read pointing it to, and need to do heaps and then graphs and then hashing, then we can complete the data structures. Okay. Graphs are fundamental concept in computer science and mathematics. Serve as powerful tools for modeling and solving a myriad of real-world problems. As aspirants gear up for the GATE exam 2024, a comprehensive understanding of graph data structure becomes paramount. These notes aim to provide a concise and illuminating guide to graph data representations and algorithms associated with them, all of which are essential for mastering this topic in the GATE examination. My guy posted something quantum valley. A graph structure consisting of vertices and edges. The edges are sometimes also referred to as nodes, and the edges are lines or arcs that are connected to nodes of a graph. More formally, a graph is composed of a set of vertices V and a set of edges E. The graph is denoted by G of V, E. Components of a graph. Vertices. Vertices are the fundamental units of a graph. Sometimes vertices are also known as vertex or nodes. Each node or vertex can be labeled or unlabeled. Okay. Edges. Edges are drawn or used to connect two nodes of a graph. It can be ordered pair of nodes in a direct graph. Edges can connect any two nodes in any possible way. There are no rules. Sometimes edges are also known as arcs. Every edge can be labeled or unlabeled. The breadth first edge algorithm is used to search a graph data structure for a node that meets a set of criteria. It starts at the root node of the graph and visits all nodes at the current depth before. Yeah, that is true. Because just because the word depth is written, it does not mean depth first search. Depth first search is an algorithm for traversing or searching tree. Alright, depth first search is an algorithm for traversing or searching tree or graph data structure. The algorithm starts with the root node, selecting some arbitrary node as a root node in the case of a graph and explores as far as possible along each branch before backtracking. Okay, that makes sense. Time complexity is a frequency is the number of vertices and the number of edges of a graph. Parameterized complexity thinking. Yeah, I don't think nobody had googled it. Oh, there is a Wikipedia article. Never mind. Types of graphs. Null graph. A graph is known as null graph if there are no edges in the graph. Okay, no edges. Graph having a single vertex is also the smallest graph possible. Trivial graph. Undirected graph. A graph in which edges do not have any direction, that is, nodes are unordered pairs, and the definition of every edge. Directed graph, a graph in which edges has direction, that is, nodes are ordered pairs, and the definition of every edge. Connected graph, a graph in which one node from one node we can visit any other node in the graph is known as a connected graph. The graph in which at least one node is not reachable from a node is known as a disconnected graph. Okay, at least one is a point. Regular graph, the graph in which degree of each vertex is equal to k is called k regular graph. Okay. Did we define degree? No, I don't think we did. Graph in which each node, from each node there is an edge to each other node. It is a complete graph. Okay. Bipartite graph. The graph in which the graph is a cycle in itself. The degree of each vertex is 2. This is a cyclic graph. Okay. Graph containing at least one cycle is known as cyclic graph. Okay, there is a difference between cycle and cyclic graph. Okay. Directed acyclic graph (DAG). A directed graph does not contain any cycle. Bipartite graph. Oh yeah, it is a DAG. A graph in which vertex can be divided into two sets such that vertex in each set do not contain any edges between them. This is a bipartite graph. Yeah, because there are no edges between this set and there are no edges between this set. From this set to this set only the edges exist. Weighted graph, a graph in which the edges are already specified with suitable weight is known as weighted graph. Weighted graph can be further classified as directed weighted graphs and undirected weighted graphs. Representation of graph, two common ways to represent a graph: adjacency matrix and adjacency list. Okay, 40 minutes. An adjacency matrix is a way of representing a graph as a matrix of Boolean zeros or ones. Let's assume that there are n variables in the graph, so create a 2D matrix, adjacent matrix, and then having dimensions n times n. Okay, if there is an edge from vertex I to j, mark adjacent matrix ij as 1. If there is no edge, mark it as 0. Representation of directed graph to adjacency matrix: C 1 to 2 and 1 to 0 and 2 to 0. Yes, that is it. The given The given figure below shows a directed graph. Initially, the entire matrix is initialized to 0. If there is an edge from source to destination, we insert 1 for that particular adjacency matrix destination adjacency list. An array of lists is used to store edges between two vertices. The size of the array is equal to the number of vertices. Each index in this array represents a specific vertex in the graph. Okay, the index I of the array contains a linked list containing the vertices that are adjacent to vertex I. An array of lists. Okay, this is a list. This is a list. This is an array of lists. Let's assume that there are n vertices in the graph, so create an array of list of size n. Okay, adjacent list 0 will hold nodes. Nice. Representation of directed graph to adjacency list. 1 to 0, there is 1 to 2, 1 null, there is 2 to 0 null. The below directed graph has 3 vertices, so an array of list will be created of size 3, where each indicates where each Indices represent the vertices. Now vertex 0 has no neighbors. For vertex 1, it has two neighbors. So insert 0 into at indices 1 of array. Nice. Basic properties of a graph and applications and advantages. Disadvantages. That is it. This is important. And with this article, I think we'll wrap it up. Okay, we have one more thing, that is hashing, hash maps and all. A graph is a nonlinear data structure consisting of nodes and edges. The nodes are sometimes also referred to as vertices, and the edges are lines or arcs that connect any two nodes in the graph. The basic properties of a graph include vertices, nodes. The points where edges meet in a graph are known as vertices or nodes. A vertex can represent a physical object, concept, or abstract entity. Yes. For example, in the Google Maps, the vertex can be my home or a shop or a school, and the edges are roads. A real world example of a graph would be like that. Edges, the connections between vertices is known as edges. They can be undirected, bidirectional, or directed, unidirectional. Weight, a weight can be assigned to an edge representing the cost or distance between two vertices. A weighted graph is a graph where the edges have weights. Okay. Degree. The degree of a vertex is the number of edges that connect to it in a directed graph. The in degree of a vertex is the number of edges that point to it, and the out degree is the number of edges that start from it. Yes, we did that. Path. The path is a sequence of vertices that are connected by edges. A simple path does not contain any repeated vertices or edges. Okay. Cycle. A cycle is a path that starts and ends at the same vertex. A simple cycle does not contain any repeated vertices or edges. True. Connectedness. A graph is said to be connected if there is a path between any two vertices. A disconnected graph is a graph that is not connected. Planarity. A graph is said to be planar if it can be drawn on a plane without any edges crossing each other. There is a, there is a theorem, Euler's theorem for planarity or something. Bipartiteness. A graph is said to be bipartite if its vertices can be divided into two disjoint sets such that no two vertices in the same set are connected by an edge. Disjoint set union, that is something we studied. Page ranking algorithm. Alright, applications of graph data structure. In computer science, graphs are used to represent the flow of computation. Google Maps uses graphs to build transportation systems. So, an intersection of two or more roads are considered to be a vertex, and the road connecting two vertices is considered to be an edge. Thus, a navigation system is based on the algorithm to calculate the shortest path between two vertices. Shortest path, nice. In Facebook, users are considered to be vertices. If they are friends, then there is an edge running between them. Facebook's friend suggestion algorithm uses graph theory. Facebook is an example of undirected graph. In World Wide Web, web pages are considered to be vertices. There is an edge from page U to other page V if there is a link of page V on page U. This is an example of directed graph. It was basic idea behind Google page ranking algorithm. In operating system, we come across the resource allocation graph where each process and resources are considered to be vertices. Each is run from resources to the allocated processes or from requesting process to the requested resources. Leads to Yeah, this is what I was about to say. If this leads to any formation of a cycle, then a deadlock will occur. Bankers, algorithm, deadlock, and all of these things. In mapping system, we use a graph. It is useful to find out which is an excellent place from the location as well as to your nearby location. In GPS, we also use graphs. Facebook uses graphs. Using graphs suggest mutual friends. It shows the list of the following pages, friends, and contact list. Microsoft Excel uses DAG. Okay. And that is Express algorithm. We use a graph. We find the smallest path between two or many nodes. Alright. 3 minutes more. Advantages of graph representing complex data. Graphs are effective tools for representing complex data, especially when the relationship between the data points are not straightforward. They can help to uncover patterns, trends, and insights that may be difficult to see using other methods. Because it is a non-linear data structure, you can compact more information in a smaller graph. but a linear structure would take much more analysis and all. Efficient data processing graphs can be processed efficiently using graph algorithms, which are specifically designed to work with graph data structures. This makes it possible to perform complex operations on large data sets quickly and effectively. Network analysis graphs are commonly used in network analysis to study relationships between individuals or organizations, as well as to identify important nodes and edges in a network. This is useful in a variety of fields, including social sciences, business, and marketing. Pathfinding graphs can be used to find the shortest path between 2 points, which is a common problem in computer science, logistics, and transportation planning. Okay, visualization graphs are highly visual, making it easy to communicate complex data and relationships in a clear and concise way. This makes them useful for presentations, reports, and data analysis. Machine learning graphs can be used in machine learning to model complex relationships between variables, such as in recommendation systems or fraud detection. We see a lot of graphs in machine learning. I have seen by myself, right? There is like a input layer, hidden layer, and output layer. They are neural networks, right? I will show that. Right. See, when you click on neural networks, the first thing that pops out is a big graph. If that makes sense. Disadvantages of graph limited representation. Graphs can only represent relationships between objects and not their properties or attributes. This means that in order to fully understand the data, it may be necessary to supplement the graph with additional information. Yes, the text can hold additional information if needed. Difficulty in interpretation. Graphs can be difficult to interpret, especially if they are large and complex. This can make it challenging to extract meaningful insights from the data and may require advanced analytical techniques and domain exposure. Asking with curiosity, can you fill the vertex with domain information to get the relationship? Graphs are actually that's okay. It is an oversimplification. Okay, it is about to click out. Then should. Okay, we are thinking in the correct direction then. Scalability issues as the number of nodes and edges in the graph increases, the processing time and memory required to analyze it also increases. This makes it difficult to work with larger complex graphs. Yeah. Scalability issues, data quality issues. Graphs are only as good as the data they are based on, and if the data is incomplete, inconsistent, or inaccurate, the graph may not accurately reflect the relationship between objects. This is actually true for any of the data structure, not just graphs. So it is not just a graph alone drawback. It is a drawback of the entire data. Lack of standardization. There are many different types of graphs, and each has its own strengths and weaknesses. This can make it difficult to compare graphs from different sources or to choose the best type of graph for a given analysis. Okay, I don't know. I mean, this is also a generalization and oversimplification, as ChatGPT has told. Privacy concerns. Graphs can reveal sensitive information about individuals or organizations, which can raise privacy concerns, especially in social network analysis or marketing. That is more of a philosophy. So we got hashing, and after hashing, the programming and data structures will be completed. Yep, small articles can be done easily. Keith, yeah, it is the same. Having said that, we will take a break of 10 minutes, people. All right, we are back. Yeah, I hope my voice is audible, and we will do another 50 minutes of stream, and then we will take a break. That makes sense. So we need to complete hashing, and I think we could be able to complete algorithms in the next class as well, if it is possible. Right, we will start. Hashing is a fundamental concept in computer science and plays a pivotal role in various algorithms and data structures. Aspiring candidates preparing for the GATE exam 2024 must grasp the intricacies of hashing to tackle complex problem solving scenarios efficiently. These notes aim to provide a concise yet comprehensive overview of hashing, covering essential concepts that are likely to be tested in the GATE examination. Hashing refers to the process of generating a fixed size output from an input of various size using the mathematical formulas known as hash functions. This technique determines an index or location for the storage of item in a data structure. Need for hash data structure every day. The data on the internet is increasing multifold, and it is always a struggle to store this data efficiently. In day-to-day programming, this amount of data might not be that big, but still it needs to be stored, accessed, and processed easily and efficiently. A very common data structure that is used for such a purpose is the array data structure. Now, the question arises: if array was already there, what was the need for a new data structure? The answer to this in the word efficiency. Although storing an array takes often time, searching it takes at least of login time. This time appears to be small, but for large data set it can cause a lot of problems, and this in turn makes the array data structure inefficient. Is it really O of log n or O of n? Okay, are we doing okay, sorted array? Yep, systems level. So now we are looking for a data structure that can store the data and search in it in constant time. I know of one time that is a hashing data structure came into play with the introduction of hash data structure. It is now possible to easily store data in constant time and retrieve them in constant time as well. Components of hashing. There are majorly three components of hashing. Key. A key can be anything, string or integer, which is fed as input in the hash function, the technique that determines an index or location for storage of an item in the data structure. Hash function. The hash function receives the input key and returns the index of an element in an array called a hash table. This index is known as a hash index. Hash table. Hash table is a data structure that maps the values using a specific function called a hash function. Hash stores the data in an associative manner in an array where each data has its own unique index. How does hashing work? Suppose we have a set of strings A, B, C, D, F, G, and we would like to store it in a table. Our main objective here is to search or update the values stored in the table quickly in one time. And we are not concerned about the ordering of strings in the table, so the given set of strings can act as a key, and the string itself will act as a value of the string. But how to store the value corresponding to the key? We know that hash functions, which is a mathematical formula used to calculate the hash value, which acts as the index of the data structure where the value will be stored. Let's say, okay. Now suppose assume that we have a table of size 7 to store these strings. The hash function that is used here is the sum of characters in key mod table size. We can compute the location of the string in the array by taking some string mod 7. Alright. The above technique enables us to calculate the location of a given string by using simple hash function and rapidly find the value that is stored in the location. Therefore, the idea of hashing seems like a great way to store key value pairs of the data in a table. What is a hash function? Okay, so the timing is mapped to 1233. The hash function creates a mapping between key and value that is done through the use of mathematical formulas known as hash functions. The result of the hash function is referred to as a hash value or hash. The hash value is a representation of the original string of characters, but usually smaller than the original. Okay. For example, consider an array as a map where the key is the index and the value is the value at the index. So for an array, if we have index I, which will be treated as a key, then we can find the value by simply looking at the value at a of I. Simply looking up a of I. Types of hash functions, because you can get the index directly. That is the main idea behind hash. What is this? Yeah, this is. All right. Competitive programming. Some guy. Okay, my guy is doing some God's work. We will come over there sooner. No worries. There are many hash functions that use numerical or alphanumerical keys. The article focuses on discussing different hash functions: division method, mid-square method, folding method, multiplication method. Properties of a good hash function that maps every item into its own unique slot is known as a perfect hash function. We can construct a perfect hash function if we know the items and the collection will never change. But the problem is that there is no systematic way to construct a perfect hash function given an arbitrary collection of items. Fortunately, we will still gain performance efficiency. Even if the hash function is not perfect, we can achieve a perfect hash function by increasing the size of the hash table so that every possible value can be accommodated. As a result, each item will have a unique slot. Although this approach is feasible for a small number of items, it is not practical when the number of possibilities is large. So we can construct our hash function to do the same, but the things that we must be careful about while constructing our own hash function. A good hash function should have the following properties: efficiently computable, should uniformly distribute the keys. Each table position is equally likely. Wait, each table position is equally likely for each. Okay. Should minimize collision, should have a low load factor, number of items in the table divided by the size of the table. Complexity of calculating hash value using the hash function. Time complexity is often wait it depends on the format simple modulus version. Okay, length of the key. Okay. Alright. If we consider the above example, the hash function we used is the sum of the letters, but if we examine the hash function closely, then the problem can be easily visualized that for different strings, same hash function is being generated by the hash function. For example, a, b, and b, a both have the same hash value, and the strings c, d, and b a also generate the same hash value, etc. This is known as a collision, and it creates problem in searching, insertion, deletion, and updating a value. What is collision? The hashing process generates a small number for a big key. So there is a possibility that two keys could produce the same value. The situation where the newly inserted key maps to an already occupied, and it must be handled using some collision handle technology. Technology. Okay, how to handle collisions? There are mainly two methods for handling collisions: separate chaining and open addressing. Separate chaining. Okay. The idea is to make each cell of the hash table point to a linked list of records that has the same hash function value. Chaining is simple but requires additional memory outside the table. We have given a hash function and we have to insert some elements in the hash table using a separate chaining method for collision resolution technique. Alright. Mhm. Open addressing. In open addressing, all elements are stored in the hash table itself. Each table entry contains either a record or nil. When searching for an element, we examine the table slots one by one until the desired element is found, or it is clear that the element is not in the table. Linear probing. In linear probing, the hash table is searched sequentially that starts from the original location of the hash if in case the location that we get is already occupied, then we check for the next location. Quadratic probing is an open addressing scheme in computer programming for resolving hash collisions and hash tables. Quadratic probing operates by taking the original hash index and adding successive values of an arbitrary quadratic polynomial until the open slot is found. This method is also known as mid-square method because the method will look for ith probe slot and ith iteration, and the value always start from the original hash function if only. Let hash x be the slot index computed using the hash function and n be the size of the hash table. As the slot hash x full hash x plus 1 square. That makes sense. Double hashing is a collision resolution technique in open addressed hash tables. Double hashing makes use of two hash functions. The first hash function, h1k, which takes the key and gives out the location of the hash table. But if the new location is not occupied or empty, then we can easily replace our key. But in the case the location is occupied collision, we will use secondary hash function h2k in combination with the first hash function to find a new location for the hash table. The combination of hash functions is a form is a non-negative example insert. All right. Nice. Double hashing, we just use two functions, that's it. The load factor of a hash table can be defined as the number of items the hash table contains divided by the size of the hash table. Load factor is the decisive parameter that is used when we want to rehash the previous hash function or want to add more elements to the existing hash table. It helps us determine the efficiency of the hash function. That is, it tells whether the hash function which we are using is distributing the keys uniformly or not in the hash table. Total elements in the hash table by size of hash table. Rehashing, as the name suggests, rehashing means hashing again. Basically, when the load factor increases to more than its predefined value, the default value of the load factor is 0.75. The complexity increases. So to overcome this, the size of the array is increased, doubled, and all the values are hashed against and stored in the new double-sized array to maintain a low load factor and low complexity. Applications of data structures. Hash table data, hash data structure. Hash is used in databases for indexing. Hash is used in disk-based data structures. In some programming languages like Python, JavaScript, hash is used to implement objects. Real-time applications of hash data structure. Hash is used for cache mapping for fast access to the data. Hash can be used for password verification. Okay. Hash is used in cryptography as a message digest. Rabin-Karp algorithm for pattern matching in a string, calculating the number of different substrings of a string. Advantages of hash data structure. Hash provides better synchronization than other data structures. Hash tables are more efficient than search trees or other data structures. Hash provides constant time for searching, insertion, and deletion operations on average. Disadvantages for hash data structure. Hash is inefficient when there are many collisions. Hash collisions are practically not avoided for a large set of possible keys. Hash does not allow null values. Hash. I thought of searching something actually. Yeah, I did not remember what that is, but Rabin Corp. All right, nice. Asymptotic analysis. Hey, we completed data structures, people, and congratulations to myself on completing data structures. Now we will move towards algorithms. Yep, this is easy actually. Okay, C program. Do we have this lab? For God's sake. I don't think we have that lab, right? Right, let's see. DWDM, we have that. DNS, we have that. FM native flat, formal languages, and automata theory. Formal languages. Object oriented analysis and design, okay. We have that as well. UML, artificial intelligence, okay. MPMC microprocessors and microcontrollers 8086. Quantum computing, okay. Data mining lab, okay. CNS lab, FSD2. That is the two things, right? Yep. 3.1 UI using Flutter. You got compiler design, cloud computing, cryptography and network security, software testing methodologies, STM, cyber security, that is a theory as well, DevOps, machine learning, software project management. I think there are some professional electives, mobile ad hoc networks, natural language processing, NLP, big data analytics, okay, media, distributed operating systems, okay, cloud computing lab, Hadoop, Apache 2, alright, cryptography, blowfish, technical paper writing. Uh-huh. We got deep learning here in 4.1. Okay, software architecture and design, patterns, okay, blockchain technology, augmented AR and VR, okay, IoT, agile, okay, yep, generative AI, alright, computer vision, okay, cyber physical systems. Yeah, you can study if you want constitution. Cryptography and network security. Do we have geeks for geeks? Yes, sir. Ad hoc. Mobile ad hoc networks. Nice. And generative AI. Nice, dude. Mhm. Britannica. It's a dictionary, right? Six minutes. Alright, guess I need to take a break. It is 12:15 already, right? Having said that,